Yes. Okay, here oxidation. Okay, here oxidation means growing the silicon dioxide on the vapor. Okay, here silicon dioxide is the insulation layer, or it is also called dielectric material on the vapor. To isolate between the uh, terminals means source and drain, or here collector, emitter, base, these terminals. To isolate between the beside terminals, we can use the silicon dioxide, okay, insulation layer. Okay, during the process of IC fabrication, when silicon is exposed to oxygen or water vapor at high temperature, okay, here oxidation, okay, can be done using the oxide. Okay, silicon, here if you take silicon as vapor, and if we allow oxygen, okay, oxygen, then we can call it as a dry oxidation. Here oxidation process is two types. Two types. First one is dry oxidation. Dry oxidation. Next one is wet oxidation. In the dry oxidation, we will use silicon, that is vapor, and oxygen. Okay, we will allow some oxygen gas. Then we get silicon plus O2, oxygen gas. We will get SiO2, that is silicon dioxide layer. Next, in the okay, this is dry oxidation. Whereas in wet oxidation, okay, silicon, that is vapor plus water, H2O, water. Then we will get silicon dioxide plus oxygen gas, SiO2 plus 2H2. Here oxygen, nitrogen. Okay, like this, oxidation process can be done. Okay, this process is called the, we can call it as a thermal or wet oxidation. Okay, next one is uh, diffusion. Okay, here what is diffusion? Diffusion is this process consists of the introduction of a few tens to several micrometers of the impurities by the solid state diffusion of dopants into selected regions of a vapor to form junctions. Here diffusion is the process of introducing the control amounts of dopants into semiconductor is called diffusion. Means introducing the dopant material, okay, to a semiconductor material. Either if we dope with p-type semiconductor, we can get we can call it as a p-type dopants, or if we dope with n-type, we can call it as n-type dopants. Okay, based on the type of transistor. Okay, we will use n diffusion or n plus diffusion, p diffusion or p plus diffusion. Here diffusion is carried out in furnace, where inert gas containing dopant is passed through the vapor at temperature range 800 to 1200 degrees centigrade. Okay, we can pass the gas, that is ions. Dopant is passed through that much temperature in the furnace, so that these ions diffused into the semiconductor. Diffusion of boron into silicon produces p-type silicon, where here boron is the p-type semiconductor. And diffusion of arsenic or phosphorus into silicon produces, okay, p-type semiconductor. Means if we want to dope with different materials, okay, we will use diffusion. At high temperature, we will put the wafer or substrate in the some furnace, and we will increase temperature, and that dopant material will get melt. That ions will be diffused into the semiconductor. Next one is ion implantation. This ion implantation. This is a process of introducing dopants into selected areas of the surface of the wafer by bombarding the surface with high energy ions of the particular dopants. Okay, here with high energy bombarding the surface of the wafer. Okay, here also we will use high temperature furnace. Here this ion implantation is the process of introducing high energy charged particles into the substrate is called an ion implantation. Okay, it produces extremely thin, selectively placed doped layers. Okay, for a particular area, if you want to implant, means deposit some material. Okay, some dopant materials, you will use this ion implantation. Ion implantation is preferably when small areas are to be doped at lower temperatures. Okay, whereas diffusion we will use high temperatures, but in the ion implantation we will use lower temperatures, but small areas. Okay, if you want to dope in the small area, we will use ion implantation. Whereas if you want to dope larger area, we will use diffusion. But in the ion implantation, we will use lower temperatures. Here ion implantation is carried out by electrically accelerated charged ions of desired impurity atom are implanted into the substrate for obtaining the desired dopant concentration profile. And next one is photolithography. Okay, these are all the broadly main steps in the fabrication. Here photolithography is the in this process the image on the reticle is transferred to the surface of the wafer. In the photolithography, uh, when we apply photoresist and when we use UV light, we will use one mask. Using that mask, we will apply some patterns. We will apply some patterns on the wafer, so that using that patterns, we will fabricate the layer by layer. In the photolithography, this applying photoresist and applying UV light, removing photoresist and forming window. These are all come under photolithography process. Next one is epitaxy. Epitaxy. Epitaxy is the process of the controlled growth of a crystalline doped layer of silicon on a single crystal substrate. Generally this epitaxy layer is formed when we fabricate the bipolar junction transistor BJTs, NPN, PNP, and we want to fabricate this bipolar transistors. We will use epitaxy layer. For the growth of a crystalline doped layer. Next one is metallization and interconnections. Here what is metallization? After all semiconductor fabrication steps of a device or of an integrated circuit are completed, it becomes necessary to provide metallic interconnections for the integrated circuit and for external connections to both the device and to the IC. This is a process of formation of metal films for interconnections. Generally, we will use ohmic contacts and rectifying metal semiconductor contacts we will use. Okay, here connection between the semiconductor and metal. So that's why we will use metal contacts, ohmic contacts. Here generally the methods used for making metal films are you will use chemical vapor deposition or physical vapor deposition. Some deposition techniques are there for this metallization and interconnections. Okay, that is chemical vapor deposition, CVD, chemical vapor deposition or physical vapor deposition, PVD. These techniques, okay, used to metallize these transistors. Slide we will see. Here, this is thermal oxidation. Okay, yeah, oxidation generally there are two types: wet oxidation and dry oxidation. In the dry oxidation, we will allow oxygen gas into the furnace to form SiO2 layer. Whereas in the wet oxidation, we will use water H2O to form the SiO2 layer on the surface of the vapor, silicon vapor. Okay, here thermal oxidation means we will use gas. Okay, here we will use gas. Here, okay, here we will apply here gas. Okay, here gas will come out. Okay, here temperature, furnace or tube. Okay, fuel lens, burner. Okay, here, okay, here we will use this wafer. Okay, here silicon dioxide, as we shall see later, plays an important role in shielding of the surface so that dopant atoms by diffusion or ion implantation may be driven into other selected regions. Okay, here oxygen or H2O carrier gas. Okay, here we will use the vapors. Okay, this is a boat. Call it this is boat. Here we will keep vapors. Okay, at particular this temperature. Okay, this layer will be formed. Okay, here like this. Okay, this SiO2 layer will be formed like this in the thermal oxidation process. Either we will use oxygen or H2O furnace. Not clear. Okay. Okay. This is the thermal oxidation uh, process. In this, we will use oxygen or H2O. Okay. Here we will put vapors. Here we will put vapors. Okay. Uh, okay. These are the This beside these are the heaters. Okay. To heat at particular temperature. Okay. Here these are silicon vapors. Okay. How much thickness we want based on the okay time and concentration we will put. Okay, we will apply this resistance. Okay, heaters. Next one is etching. Okay, here what is etching? Okay, here etching is the process of selective removal of regions of a semiconductor metal or silicon dioxide. Okay, here etching means in the vapor if you want to remove the particular area or region, okay, then we will use getting voice is not clear. Sri Lanka, is it clear? Okay. Okay. Hmm. Here, etching is the process of removing of the selected area or particular region. If you want to remove that area, okay, we will use etching process. Okay, here also etching is two types: wet etching and dry etching. Okay, in the last class we saw applying UV light and removing the some portion. Okay, we call it as a window type that picture by using this etching process. Okay, in wet etching we will use some chemical solution, but whereas in dry etching, okay, we will apply some gases. Okay, uh, in wet etching, the vapors are immersed in a chemical solution at a predetermined temperature. Okay, in this process, the material to be etched is removed equally in all directions so that some material is etched from regions where it is to be left. This becomes a serious problem when dealing with small dimensions. Means here what is the problem in wet etching is, okay, if we keep on immersing this vapor in the solution, some area may be removed deeply and some area removed lightly. Okay, and not even etching is sometimes it may not etch it properly. Okay, because of that, and for especially in small okay dimensions. Okay, this etching some sometimes serious problem. Okay, next in dry or plasma etching, the vapors are immersed in a gaseous plasma created by a radio frequency electric field applied to a gas such as argon. Electrons are initially released by field emission from an electrode. These electrodes gain kinetic energy from the field, collide with and transfer energy to the gas molecules, which results in a generating ions and electrons. Okay, here okay, we will use at high temperatures. Okay, a gas such as argon. Okay, by applying the high voltage. Okay, this kinetic energy will be formed and collide with beside atoms, transfer energy. so that here more number of ions are formed, and we can remove that particular area using this plasma etching by applying these particular gases. The wafer to be etched is placed on an electrode and is subjected to the bombardment of its surface by gas ions. Okay, as a result, atoms at or near the surface to be etched and removed by the transfer of momentum from the ions to the atoms. Okay, because of this high energy, these atoms, ions are etched. Okay, ion by ion, here atoms are etched away from the surface of the vapor using this plasma etching. Next one is diffusion. Okay, here what is diffusion? Okay, here diffusion. Most of this diffusion process occurred in two steps. Okay, pre-deposition and dry in diffusion. Okay, here what is pre-deposition step? Okay, high concentration of dopant atoms are introduced at the silicon surface by a wafer that contains the dopant at a temperature of about 100 degrees centigrade. Means, as previously I told, same you will keep in a okay at high temperature furnace, and we will apply dopant material at high temperature. This dopant material will uh, applied on the silicon surface. Okay, so this here diffusion will occur at the temperature of 1,000 degrees centigrade. Silicon atoms move out of their lattice sites, creating high density of vacancies and breaking the bonds with the neighboring atoms. Okay, these are all at particular temperatures. Their okay bonds may break. Okay, then their these dopant materials may diffused into that silicon vapor. The second step is drive-in process. Here also this used to drive the impurities deeper into the surface without adding any more impurities. Okay. Uh, okay. Here also same you will use at high temperature process, and next here I told for N-type and P-type impurities dopants, boron and antimony phosphorus for the N-type. Here same this is diffusion. Okay, it is like a oxidation process. Here we will use silicon vapor, same. Here liquid impurity source. Okay, we will keep the dopant material here. Here furnace. Okay, here heaters, here and here heaters. Okay, at high temperature this okay, and we will apply some gases here. Okay, here some gases here and there. Okay, because of this high temperatures, their their bonding beside atoms bonding break, and these ions will okay deposit onto this surface of the vapor. That is called diffusion. Slide we will see. Here process. Okay, which gases will apply? Nitrogen, oxygen. These are all there. Here ion implantation. To generate ions such as those of phosphorus or narc, discharge is moved to occur in a gas. Okay, we will see this image. Hmm. Okay, this is ion implantation. Here we call it as a chamber anode. Okay, here plasma will use here gases, some gases. Okay, here ion source means which material we want to deposit on the vapor. Okay, we will put here ion source. Okay, here two sides we will keep magnet. Okay, their direction from their source to your destination. Okay, they may not okay go besides their walls, so you will use some magnets here. Okay, here also you will use some magnets. Okay, and we will apply plasma at high temperature. These ions, source ions, means dopant ions, okay, will flow like this ion by ion and deposit here in the substrate material. Here ion concentration column, here this one. Some for this movement of these ions will use some magnets here for direction. Okay, and here some filaments are also there. Okay, we'll keep here we will apply some heat. Okay, your cathode is the filament. Okay, by keep on increasing your temperature voltage, the source ions okay will move from source your station to okay like this, and it will form okay ion by ion and the vapor here. Okay, for small dimensions we will use this ion implantation. Hmm. Okay, what are the advantages of ion implantation? Okay, doping levels can be precisely controlled since the incident ion beam can be accurately measured as an electric current. Means here applying ion by ion, so doping's level can be precisely controlled, and the depth of the dopant can be easily regulated by control of the incident ion velocity. Okay, by controlling this ion velocity we can depth of the dopant material can be controlled, and extreme purity of the dopant is guaranteed. Means here we are depositing okay ion by ion, so their concentration and purity of the dopant is guaranteed. Next, fourth point, the doping uniformly across the surface can be accurately controlled. Ah, okay, even uniformity of the surface of the vapor okay can be accurately controlled, and because the ions enter the solid as a directed beam, there is very little spread of the beam, thus the doping area can be clearly defined. Yeah, here these are the advantages. By using this we can evenly uniformed surface doping can be okay, applied. Okay, since this is a low temperature process, the movement of impurities is minimized. Okay, here we will, okay, minimized impurities we can apply. If you see here, these are the, when we apply